This is my lab video for Lab 3, Magnetic Field of a Bar Magnet by Julian Perez. The purpose of this experiment was to determine the value of n in the equation B equals k r to the n. This value n tells you the exponent for the input r, which is the distance from the magnet. From this experiment, we also get the value k, which has to do with the magnetic moment of the magnet. Using this information, the next step would be to use computational means, by which I mean Python, to determine the experimental value of the magnetic field at a 45-degree angle. To perform this experiment, the main physics concepts used were Biot-Savard's law, which relates the distance from a specific observation point to the magnet and the magnetic field at that observation point. In order to do this, a magnet was placed at the end of a meter stick, and my phone was used to calculate the magnetic field at each point along the meter stick. The orientation of the phone and the magnet and the meter stick were oriented to cancel out the Earth's magnetic field so that it would not interfere with the experiment. The phone was moved along the meter stick, and then the average distance after 3 trials was measured for the following magnetic field strengths: 20, 70, 120, 170, and 220 microteslas. The following were the observed distances at each of the specific magnetic field strengths, and the averages were then calculated. Through algebraic manipulation, the n exponent can be brought down and then used in this following equation, which relates the natural log of the field strength to the natural log of the distance, and the slope of the line is actually the value of n. My experimental data showed that the value of n was negative 3.27, and according to the equation, it should be negative 3, so this is decently close. Next, I used a Python script to simulate the magnetic field at 6 different points around the bar magnet. The 2 orange arrows are the axial observation points, while the cyan arrows are all perpendicular. Next, using this, I was able to calculate the magnetic field strength at a point 45 degrees from the axial distance, and I increased the length of this arrow so that it would be visible, as its magnitude was a lot less than the other arrows. I then performed the experiment for the off-field magnetic force. However, there must be some error done in my experiment, as the value differs greatly from the value calculated by Python. For this reason, I believe that there are many factors that could have come into play, from me not orienting the meter stick correctly the second time around, along with the tapes being misplaced on the iPhone, or even possibly magnetic interference from other objects in my house. If I were to repeat the experiment, I would most likely do it outside so that I can avoid any magnetic interference that would occur inside my house, and also double and even triple check that I have the orientation correct with respect to the Earth's magnetic field. If I had not oriented the experiment in order to compensate for the magnetic north, and instead just laid out the experiment at some intermediate angle with respect to Earth's magnetic field, the results would have changed, as I am basically adding the vector, which I do not know the direction nor exact magnitude of the Earth's magnetic field at the observation, as I move it along, and if it is not parallel to this vector, then my results would be constantly changing throughout. Given that I am measuring the magnetic field at distances very far from the magnets, or relative to the magnets very far, I would expect the 2 magnets to behave more like one large magnet of double the magnetic moment of one magnet. As a result, I would expect my measurements to differ by a value of 2, as my new measurements would be twice as great as the previous one.